We have Arundhathi Krishnan, who is coming from Ireland, of course online, and will tell us about project related to non-commutative probability. And you see the formal title, so take it away, Arundhathi.
Thanks very much for the invitation to speak in this online seminar. I'm quite aware that it's a different audience and I might end up over-explaining some things and maybe not explaining some things enough. So I apologize if there's too much detail, and please stop me if I should be a little slower about anything. So the title, my talk is there. I'll be talking about a central limit theorem in the framework of a group known as Thompson's group F. And okay, let's make sure I'm actually able to go down on my slides. Sorry, just a moment. I should have checked that out. I'm just trying to get to the next slide, I'm sorry. Okay. Oops. Okay, very good, sorry. So here's a brief outline of my talk. I'll talk for a little while about algebraic central limit theorems. So by this, I mean I'll talk about central limit theorems in a non-commutative context. I'll start with the classical central limit theorem and how it fits in to this more general notion of algebraic central limit theorems. I'll say a little bit about the Thompson group F, and then I'll state and give a sketch of a proof of a central limit theorem in the context of the Thompson group F. So let's start with the classical central limit theorem, which is the well-known theorem that says that if you have a sequence of independent and identically distributed random variables xn, and for simplicity's sake, we'll assume that each of them has mean 0 and variance 1, then this normalized average Sn, which is 1 over square root of n, multiplied by the sum of the first n random variables, will converge in distribution to x, where x is a random variable with the standard normal distribution with mean 0 and variance 1. So the normal distribution has the probability density function given here, 1 over square root 2 pi e to the minus x squared divided by 2, and there's a picture of what the probability density function looks like. So I'll just say something quick about convergence in distribution. So we'll say that a sequence of random variables yn converges in distribution to a random variable y, denoted this way, if we have convergence of the respective cumulative distribution functions. So this is where I wanted to see if I can annotate. So I can, and I will. But of course, this just means that mu of yn less than or equal to x converges to mu of y less than or equal to x for all x where fy is continuous, and mu is the probability measure. So you have yn going from omega to r, and mu is the probability measure on omega. So this convergence and distribution is equivalent to many other conditions. But the condition I want to talk about is the fact that it's equivalent to the convergence of the expected value operators. So the expectation of f of yn will converge to the expectation of f of y for all bounded continuous functions f. And in particular, it will also mean that the expectation of yn to the d, so if I take the dth powers of yn, the expectation will converge to the expectation of y to the power d for all d in n. And I'm going to come back to this condition because we'll use it to define convergence and distribution in the algebraic context. Okay. So I'll go to the next slide. So I'll now give the setup of an algebraic probability space or a non-commutative probability space. So we'll say a star probability space or a non-commutative star probability space is a pair M psi, where M is a unital star algebra and psi is a unital positive linear functional on M. So the algebra M has an identity element, so it's unital, and it has an involution given by star, and a unital positive linear functional psi is linear. So psi of alpha x plus y is alpha psi x plus psi y, It seems like the annotations stay on. I'm sorry that I'm discovering things like this. I'm just going to delete all of that. Sorry. So unital positive linear functional means that psi is linear. Psi of the identity of M is 1. And psi of all positive elements which have the form x star x is greater than or equal to 0. So that's the positive part, the unital part, and the linear part. So pair M psi is what will now be a star probability space for us. And some important examples of star probability spaces. The first one is we look at square matrices, and the normalized trace will be the linear functional, the unital linear functional. And another important class of examples is where you have G to be a group. You take CG to be the group algebra, and phi to be the canonical trace given by delta G equal to E. So we just mean that phi of the identity is 1, phi of x is 0 for all x not equal to the identity, and then you extend this linearly to the group algebra CG. So this is the group algebra of the Thompson group F, and this canonical trace is what we'll work with, but I'll come back to that a little bit later in the talk. Okay, I have to remember to clear all my drawings and then go to the next slide. Okay, but well, how does our classical? Yeah.
Sorry, can you get back to the previous slide and explain once again what is the canonical trace here in the WASP example?
Yeah. Of course. Sorry, I'm just a bit slow with the annotations because I need to keep selecting it. But anyway, so it's just we'll define the functional to be equal to 1 for the identity, and then you define phi of x. For every other group element, you define it to be 0. So for every x that's not equal to the identity. And then you can extend this to the entire group algebra. So this is just defined on group elements. This is for x in the group G. And then you extend phi to the group algebra in a linear way. So phi of a linear combination of elements will just be the corresponding linear combination. Is that okay?
Yeah, sure.
So it's called the canonical trace because what you can do with the group algebra is to impose a topology on it and then look at what is known as the left regular representation and the corresponding von Neumann algebra. And there you'll get a trace on the von Neumann algebra given the analytic structure there. And so that's why it's called the canonical trace. That's where the terminology comes from. But just at the group level, you define it to be 1 at the identity and 0 everywhere else. So I've just been clearing the drawings because it seems to stay on in the next slide, as far as I can see. Okay. All right. So anyway, we want our classical probability space to fit into this algebraic framework because you want to generalize the classical probability space, and it's fairly easy to see how that happens. So if you have a probability space as we usually think about it is a triple. So omega is a sample space, sigma is a sigma algebra, and mu is a probability measure. So what we do is to take L to be the L infinity space of this probability space. Then this is a star algebra, which is in fact commutative. So the elements are just functions and they commute with each other. The multiplication is just pointwise. And the linear functional that we consider, we also write that as trace mu of f. And this is just the integral of f with respect to the probability measure mu. So then this pair, L trace mu, is a star probability space in the way that we defined a star probability space, except that the star algebra here is commutative, whereas in general, it doesn't have to be commutative. But just a word of caution here is that sometimes we may not work with the star algebra L infinity. We might work with this L infinity minus space, which is given to be the intersection of all LP spaces over P greater than or equal to 1. And the reason we do this is that a random variable with the normal distribution is not essentially bounded. It doesn't belong to L infinity, but all of its moments are finite, which means that, I'm going in the wrong direction, which means that it'll belong to LP for every P, and therefore it'll belong to the algebra L infinity minus. So depending on the context, we might have to choose our star algebra wisely, let's say. So the classical probability space fits into this algebraic framework. And the next notion that we want to generalize is the notion of a random variable. And we usually think of a random variable as some real valued measurable function on the sample set with respect to the sigma algebra. So in a star probability space, which is the pair M psi, a non-commutative random variable is just an element of that star algebra. And we'll often assume that the element is self-adjoint. So let me just add that there. And that's to correspond to the fact that a random variable is often thought to be real valued. So often we'll take X to be X star. So it's self-adjoint with respect to the involution on the star algebra N. Okay. And here also we will define the notion of convergence in distribution. So we take AN phi n to be a sequence of star probability spaces and A phi to be another star probability space. And we take this sequence of random variables, which just means elements AN, little an of capital AN, each of which is self-adjoint. And we'll take X to be an element of A, another random variable. So we'll say that the sequence AN converges in distribution to X and denote it this way. If the limit as n goes to infinity of phi n AN to the D. So this is saying you look at the Dth moments and then look at the limit as n goes to infinity. That should be the Dth moment of X. So the way you want to think of these linear functions, phi n and phi, is that they're really generalizing the notion of the expectation functional in classical probability. That's the role it's playing here. Okay. So a few slides ago, when we looked at an equivalent characterization of convergence and distribution in the classical setting, I mentioned that we would be looking at the expectation of the Dth powers of the functions converging to the expectation of the Dth power of the limiting function. So that's what gives us this definition of convergence and distribution in this algebraic setting. Okay, and then we'll define tensor independence. So this is just classical independence as we know it, which means that the probability distribution of the product of these random variables which are independent will factorize. So this is just that notion. It's called tensor independence here because the star algebra M itself may not be commutative, but we'll say a sequence of random variables AN and M is tensor independent if AI, AJ is AJ, AI. So all these random variables commute with each other for all IJ and N. And phi of this product, which means you want to think of this as the distribution, the joint distribution of this of these elements AN1 to the power M1 up to ANK to the power MK, that factorizes. So I'll just remind you that phi is just a linear functional. It's not necessarily multiplicative. But suppose phi satisfies this condition for the sequence AN, then the sequence AN is said to be tensor independent. But the way we want to think about this is that we can get the joint distributions of the sequence AN as a product of the individual distributions of each ANI. So the joint distribution is, you can know that completely if you know the individual distributions. And that's something that we have in the classical setting if we have an independent sequence of random variables. So we have this notion of tensor independence. And what we can do now, let's clear my drawings and go to the next slide. What we'll do is to state the same classical central limit theorem, but in this algebraic context. So it's the same theorem, but just stated in the setting where you have A phi to be a star probability space. And we'll assume that A is commutative. So you can think about it as our function space as we do in the classical setting. And suppose you have AN equal to AN star, a sequence of self-adjoint tensor independent, which is what we just defined, and identically distributed random variables. And again, we'll assume for the sake of simplicity that phi of AN is 0. So that's saying, I'm just going to add here that this means So you think about this as the mean, and then phi of an squared is the variance. So mean 0 and variance 1. Then if you take Sn to be the same sequence, 1 over square root n, a1 plus up to an, the sequence will converge in distribution to x, where x is a normally distributed random variable of mean 0 and variance 1. So we're saying that the limiting distribution of a sequence of IID random variables is the normal distribution, except that we've restated the theorem here in this algebraic setting. Okay, so let me give my drawings and go to the next slide. So just a note here, this formulation of algebraic convergence and distribution might seem like it's a weaker condition than convergence and distribution as we know it in classical probability. But the normal distribution is actually completely determined by its moments. So it's enough to know convergence of moments to say that you actually have convergence and distribution. So this is just to say that what has been stated here in this algebraic setting is equivalent to the classical central limit theorem. But anyway, the advantage of stating the theorem this way is that we can now replace A phi by any star probability space where A may not be commutative anymore, and then consider what property can you give the sequence AN such that you still get some kind of central limit theorem. And I suppose the most well-known of the central limit theorems, at least in the world of operator algebras, is the free central limit theorem, which gives a central limit theorem for a sequence of freely independent random variables. So I'll define what free independence is. So we're going to replace this classical independence of the sequence AN by some other property. And that property that we're first going to look at, or the property looked at by Voiculescu in the 1980s, was the notion of free independence. So the definition of free independence, I suppose if you look at it, it doesn't seem immediately intuitive, but let's have a look anyway. A sequence of random variables AN and A. So A is just a star algebra here. You'd say AN is freely independent if the following happens. So we first take capital AI to be, you can talk about the star algebra generated by the identity and little ai. So what we want is that we want phi of this product x1 to xk to be 0 for all k and n whenever the following happen. Phi of each xj is 0. What are these xj's? Each xj comes from the star algebra capital Aij. And the third is the important condition, which says that, let's say x1 comes from AI1, x2 comes from AI2, and so on. But these neighboring indices should not be equal to each other. So I1 not equal to I2, I2 not equal to I3, and so on, up to the last pair of indices. So if whenever these three conditions occur, so phi of the individual random variables is 0, then phi of the product is also 0. In this case, we say that AN is freely independent. So Voiculescu was looking at free independence in the context of looking at the free product of groups. And he showed that if you have a free product of groups, then the corresponding group algebras will be freely independent in the group algebra of the free product. So this was the context in which he started to look at this. But just to say that maybe the thing we should take away from here is that free independence is a natural sort of universal property in the sense that just like in tensor independence, the joint distribution of a sequence of freely independent random variables will also depend only on the individual distributions of each random variable. So it won't just factorize like in the case of the classical setting, but here also the joint distributions are determined by the individual distribution. So this is the key takeaway here. And well, now that we've defined free independence, I promise there will be something. Sorry.
Can you see that easily, that the joint distributions are determined, or no?
Yeah, no, I think there's a fairly easy to show lemma which kind of shows you this, and then you can see it in the case, you just start with the joint, phi of x1, x2, and you can sort of work it out for the smaller. You can work out the exact relation for the smaller k. So phi of x1, x2 or phi of x1, x2, x3. But I don't actually, like, I can't remember. I won't be able to go over the proof right now, but maybe this is a good time to say that a reference for a lot of what I'm saying is this book, which is probably not visible, but I'll say it's the book by Nika and Speicher called Lectures on Free Probability. It's also available online, so I can leave a link to that. And I was just going to say that I will very soon come to something to do with combinatorics in some sense. So hopefully I'll be sticking to the spirit of this seminar. But I think it's not too difficult to show, just to answer your question.
Okay. And also, can you give, is there some intuition about these three conditions that is easy to follow, or we should accept it for now?
Yeah, I mean, I'm sure there is good intuition. It's just I'm not sure that I will be the best person to give this. I'd say the book probably has a good exposition of it, of why this condition is quite natural. It's just I'm not sure I can give a good explanation now. But I will leave a link to that book because I think it's a very nice exposition. At least the first few chapters are quite easy to follow.
All right.
So the free CLT. So this was proved by Voiculescu in 1985, and then a combinatorial proof was given by Roland Speicher in 1990. And I believe the original proof of Voiculescu uses the notion of something called R transforms, and it's really a proof in analysis. But the proof of Speicher is sort of a counting problem, really. And it's a very nice proof, and I'll briefly say something about it. But first, the statement of the free CLT, very much in parallel with the statement of the classical CLT. So A phi is a star probability space. AN is a sequence, again, of self-adjoint random variables, which are freely independent and identically distributed. And again, we'll assume that phi of AN is 0 and, phi of AN squared is 1 for every n. Then Sn, which is the same average as always, converges in distribution to a random variable S, whose law is it's called a semicircular element. So its distribution is Wigner's semicircular distribution, where the probability density function is given here. X is 1 over 2 pi square root of 4 minus x squared. It's a semi-ellipse rather than a semicircle. So Sn. Sorry.
So does that mean that if you take this element S and you look at you take its powers and you apply phi to it, that those moments agree with the moments of the semicircle?
Yes.
Okay.
Yes, exactly.
And does this element S, is it living in some completion of A or actually in A? Sorry, not S, the element S.
The element S, which Sn converges to.
Yes.
Yeah, so I think the convergence and distribution is really talking about the value. It really only says something about what phi of Sn to the d converges to. So we're just talking about the convergence of the real numbers, the real or complex number, the scalar values phi of Sn to the d.
So it's not necessarily, there may not be an element of A that manifests this.
No. Okay. No. It just says that the distributions converge to the distributions of a semicircular element.
Uh-huh. Yeah. Thank you.
So exactly what you said, the moments converge to the moments of the semicircular distribution, which is given here. So just to say briefly what's happening when you're actually computing moments, what we're trying to look for in both of these cases is the limit as n goes to infinity of phi of Sn to the power d. And if you break down what Sn is in terms of the AIs, the random variables AIs, you just get this expression here on the right-hand side. So it's the limit as n goes to infinity of 1 over n to the d over 2. And then there's this summation over all I tuples, which are of length d. So this notation d is just, it's common enough notation, I suppose, just the set 1 to d. So the tuples of length d, which take values between 1 and n, and we're evaluating phi of this product here. Right. So this is really what computing the moment what it amounts to. It's finding this expression on the right-hand side. And as I said earlier, both tensor or classical independence and free independence give a rule for calculating these mixed moments from the values of the individual distributions. So what that means is phi of this product depends on the tuple I1 to ID only on the information which gives which indices are equal to each other and which ones are not. Okay. And the way we interpret this information is, oops, sorry, I keep jumping slides, I'm sorry. I haven't given an online talk in a very long time, I'm sorry. So the way that you encode this information is by using this a partition of the set 1 to D. And that partition is what is known as the kernel of the tuple I. So the kernel of I is just a partition of D into the leveled sets of that tuple. So this is best illustrated with an example. So I definitely want to draw some pictures here. So if we have phi of this product, I've got an A3 in position 1 and also in position 3. So I'm just going to connect up those points. And then I have no more A3s. And then A1 is in the 2nd and the 7th position. A2 is in the 4th and the 5th, and then A4 is in the 6th and the 8th. In this particular example, we actually get a partition into pairs. The pairs being the points 1, 3, 2, 7, 4, 5, and 6, 8. But in general, of course, it could be any partition. But the reason I've got pairs as an example here is that what happens is that for both tensor and free independence, the only tuples I in this sum on the top there, which will contribute to the sum, are those tuples whose kernels are pair partitions. Again, this is something that can be seen fairly easily, because you also want to keep in mind that you don't care about the actual values for every n, but the limit as n goes to infinity. So taking this into account, you can see that the only tuples that will contribute here are those whose kernels are pair partitions. And in the tensor case, all pair partitions will contribute. And in the free case, only the so-called non-crossing pair partitions will contribute. So again, I keep going back to this book, but it's really a very nice book which goes through a proof of a general central limit theorem, which actually covers both the classical and the free cases. And it's only at the very end that it breaks into two portions, one to show that you need to count all pair partitions, and two to show that you're in the free case, you're only looking at non-crossing pair partitions. So let's go again. The next slide. So I'm just going to say, it's possible that everyone here knows a lot more about pair partitions than I do, but I'm just briefly describing what it is. It's just a partition of a set into pairs. It's exactly what it sounds like. So, oops. Yeah. So a pair partition of D is just a disjoint collection of pairs, V1 to VD over 2. Each VI is a set of cardinality 2 sitting inside the set 1 to D. And the VI and VJ, these are disjoint when I is not equal to J. So it's just exactly what it sounds like. And we write the set of pair partitions as P2 of D. So I've just got an example here for a crossing pair partition of 6. So the crossing literally means that these two pairs cross each other, 1, 3, and 2, 4. And here's an example of a non-crossing pair partition where none of the pairs cross each other. And the number of all pair partitions of D can be seen quite easily to be D minus 1 double factorial, which is just D minus 1 by D minus 3 all the way up to 1. Of course, when D is odd, the number of pair partitions crossing or non-crossing is 0. And when it's even, it's equal to this. The number of non-crossing pair partitions of D is given by Catalan number.
So
C20.
This talk is very appropriate for this seminar because C20 is a background.
I was just going to say, yeah, C20 is what got me into this meeting. So yeah, the number of non-crossing pair partitions is.
I have a quick question. This vaguely reminds me of something classical that using Wigner did, in which Catalan numbers also came up, and maybe the semicircular distribution relating to random matrices. Is it any relation?
Yeah, it's the same distribution. So it's the limiting distribution of the eigenvalues of random matrices. So it's the exact same distribution.
Okay,
yes. Yeah. So the number of all pair partitions is here. The number of non-crossing pair partitions is here. And my next slide says exactly that. The number of all pair partitions of D is exactly the dth moment of the normal distribution, which is the limiting law in the classical CLT. And the D over 2th Catalan number is the dth moment of Wigner's semicircular distribution, which is the limiting law in the free CLT. And that's exactly how this combinatorial proof was given by Speicher and then later appeared in this textbook. And as Doron just said, the semicircular distribution is also the limiting distribution of the eigenvalues of a sequence of symmetric random matrices. That it's the same distribution there.
Is a direct relation? Is one a special case of the other, or is that coincidence?
Sorry, what's the question?
Is it a coincidence, or can you view the Wigner classical result as a special case of this?
No, I don't think it's a coincidence, because I think the sequence of random matrices, I think you'll get a freely independent sequence there. So I don't think it's not a coincidence. No.
So it could be viewed as a special case of this general theory.
What can be viewed as a special case? Sorry.
The classical Wigner thing is then a special case of the more general.
Oh, right, exactly. Of the limiting distribution of a freely independent sequence. Yes, I believe that's what it is. Yes. Sorry, I've slightly lost track of what I wanted to say. So yeah, there is this general CLT which works both for the classical and the free, the tensor independent and the free independent case. And a little bit later, there's a more generalized CLT, let's say, which Speicher and Voiculescu, and then also von Waldenfels, I think these were separate papers. They showed the following. You've got a similar setup. A phi is a star probability space. And then you have a sequence of self-adjoint random variables, which now, instead of satisfying some kind of independence, they satisfy an invariance principle called exchangeability. So this just means that joint distributions remain the same when you permute the indices. So this is what an exchangeable sequence of random variables is. I mean, this is a notion that exists in classical probability, and it's just generalized here to noncommutative probability. And then the second property you want AN to satisfy is the singleton vanishing property. So this means you want phi of a product of AIs to be 0 if any index appears exactly once in that product. So if there's a singleton in the product, then the distribution becomes 0. So that's the singleton vanishing property. So in this more general case where AN satisfies these two conditions, you take Sn to be the same as sampled average, then you have the limit of the dth moments can be written as sum over pair partitions of some value phi pi, which depends only on the pair partition pi. So phi pi is the value of phi of this product, where L is any tuple whose kernel is the pair partition that you chose. So just like we did for the free and the classical case, here also you can express the limit of the dth moments as a sum of some value which only depends on the corresponding pair partition. And if you go back to the original formula for the moments, the sum is something that depends on n. But by transferring it to a sum over pair partitions, the sum no longer depends on n. The value inside might, of course, but what you're summing over no longer depends on n. So this is good because it shows that it gives you the chance of actually finding a limit, or it increases the chance of finding a limiting law. Okay, so I'm just checking the time there, and I've done 34 minutes. So I'll keep going, but I'll make sure not to go over time. Stoyan gave me strict instructions. 48 minutes is the cutoff. Anyway, so I should say something about the Thompson group F. But just before that, I'll say that what has happened since all this work on CLTs is that people have tried to look at central limit theorems in different contexts for different kinds of sequences. And some of the sequences that people have looked at are sequences that arise in the group algebras that I talked about a little bit earlier. And in particular, people have looked at the infinite symmetric group, S infinity. So this is just the group of all finite permutations on N. And in 1995, Philip Bian looked at the symmetric group, and he looked at the sequence of Coxeter generators, so n plus 1, with the canonical trace that I mentioned before, and showed that there also the limiting law is Wigner's semicircular distribution. Later, much more recently, Kursler, Nika, and then Campbell, Kursler, and Nika looked at the so-called star generators, which are the transpositions 1n, and looked at a different trace in the group algebra, not the canonical trace, but some other linear functional, and showed central limit theorems in that context. In 2003, Fendler also looked at slightly more Coxeter, more general Coxeter and Artin systems of large and extra large types, and there also some CLTs were found. So, next slide. So the group that we're looking at is Thompson's group F, which has this presentation given here. It's a fairly easy presentation. There are infinitely many generators, G0, G1, and so on. The convention is to start at G0 rather than G1. And the relations satisfied by the generators are given here. You have Gn, Gk equal to Gk, Gn plus 1. So the generators don't commute with each other, but this happens for k less than n. So the generator with smaller index remains the same, but just moves over to the other side. And Gn goes over to the other side, but increases by 1. So these are the relations satisfied by F. And the context I'm going to look at is looking at the group algebra of F with the canonical trace. So phi of x is 1 if x is the identity and 0 otherwise. And you extend this to the group algebra. So just one slide about the Thompson group F itself. I should clear all these drawings. So F was introduced.
Excuse me, may I ask for the motivation for you to consider this group in particular?
Yeah. So I'm going to say something about that now. Thank you. Well, the reason for me personally is that I was already looking at some other properties in relation to Thompson's group F, and I'll just say something about that in a second. I just want to say that the presentation given there describes the group F, but the way it was introduced was as some subgroup of piecewise linear homeomorphisms on the interval 0 to 1, where the slopes of all the piecewise linear portions are dyadic rationals. So this is how Thompson looked at F, and he also considered two other groups, V and T, but the group that we're looking at is the group F. There are different ways of looking at this group in terms of morphisms on the category of rooted ordered binary trees. I'll just leave a reference there, which is quite nice. The thesis of Jim Belk has quite a bit of information on this aspect. And it's a group that's of interest to a lot of people, certainly in operator algebras, because there is this question of whether the group is amenable or not. So I know a lot of people working in C-star algebras, for instance, are interested in this group. And there's also been interested in probabilistic aspects of F. Swan Jones was studying F quite a bit, looking at various representations of F in Hilbert spaces and so on. And the context in which I was looking at this before I started this work was with some collaborators, we were looking at how F is connected to non-commutative Markov sequences. So again, in the setting of non-commutative probability, but it turns out that there's some kind of relation between representations of F and non-commutative Markov processes. So that's the context in which I was a postdoc with Ando Nika at the time at the University of Waterloo, and she suggested this question of maybe looking at a central limit theorem in this context, because we were already looking at probabilistic aspects of it. So that was my sort of introduction to the group F. But I think for people in different areas, it's interesting for different reasons.
It looks interesting because the multiplication is not non-commutative, but there is still some structure, like kind of.
Exactly. Yeah. And I think, in fact, the central limit theorem, which I'll go over, maybe not all of it, but some part of it, is that the limiting law that we get in this context is the normal distribution, even though it's not a commutative sequence. The limiting law we get is that is the law that you get in the classical setting. So there is something about those relations which seem to make that happen. So maybe I should just check how much time I have so I know maybe what slides to slip as I go on. Is it 8 minutes?
Yeah, I guess so, maybe.
Okay. So I'll probably skip most of the proof, but I'll try to give some flavor of what's going on at least. So anyway, here's the statement of the theorem. Okay, so we just need to set up what is our sequence of interest here. So AN will be the sequence of self-adjoint random variables in the group algebra of F. It's just defined in a very natural way using the generators of F. But we want the sequence to be self-adjoint. So we take AN to be Gn plus Gn star divided by the square root of 2. The Gn star here is just Gn inverse, but you view it as an element of the group algebra rather than the group. You take Sn to be our favorite old friend, 1 over square root n, sum of the first n random variables, except that we start at A0 and go up to An minus 1. And what we get is that the limit of the dth moment, it's 0 for d odd and d minus 1 double factorial for d even, where this means that Sn converges to a random variable with standard normal distribution. And maybe just to answer the previous question again, it doesn't mean that X is in the algebra C of F. We're just talking about convergence of the moments. That's really what convergence in distribution means. So again, the rough idea. So I'll try and give an idea of the proof, and I'll skip many of the slides because I've run out of time. My apologies. But again, we kind of break down the dth moment of Sn. We write the Sn in terms of the ANs, which in turn we write in terms of the generators Gn. So what it ends up looking like is a sum, 1 over 2n to the power d over 2. And then you're summing over tuples I and epsilon. So I is the index, which tells you which generator you're considering. And epsilon just tells you whether you're looking at a generator or its inverse, because epsilon can be +1 or -1. And the linear functional phi, this canonical trace, the way it's defined is that phi of this product is either 1 or 0. It's 1 exactly when the product evaluates, when this product is the identity. So what this question really boils down to is counting the number of ways you can have a product of this form, which is equal to the identity. And because I care about the length of that product being D, a useful way to think about this is what I've written here under the task. You're counting the number of words of length D composed of the first n generators of F and their inverses, which evaluate to the identity. So I'm thinking about this as a word because you're really thinking about the tuple I here. So I'll just maybe look at an example. I'll just write that here. I feel like I'm spending all my time. I don't know why my screen, my share went away. I'm coming back. Sorry, technology is not my friend today. Okay, so I'll just say that like a word, for example, could be something like G1, G2 inverse. I'm not saying that this is equal to the identity, but I'm just writing down an example. So something like this, right? I'm thinking of it as a word, but really this means this is going to evaluate to the product G1, G2 inverse, G0 inverse, G3, right? But it's useful to think about it as a word because then you can see all the possible ways in which you can have a word of length D, which will give you a product which is equal to the identity. So that's really what our task boils down to. But I'm definitely out of time to actually give the details. So I'm probably not actually going to go over the proof. Again, sorry, I just delete all these annotations. So maybe I'll say a little bit about what we're doing. What we do is to reduce every word which is going to evaluate the identity to something called a normal form. And this, again, might be something that people here are familiar with. We're going to reduce it to a word which has this really specific form where all the generators are on the left and all the inverses are on the right. And the generators are ordered in a particular way. So the details are here, but roughly speaking, we want these generators to, for the most part, be reducing. Some of the indices might say the same, or there might be an increase of 1. And then you have the exact, the mirror image of that for the inverses. And the usefulness of doing this. I'm just going to skip over all of this and go here. So this is a normal form. And the usefulness of this normal form is that you can see exactly which generator cancels with which inverse to give you the identity. And this is where the pair partition comes in, because we're pairing each generator with the inverse that cancels it out in the normal form. But what you can do is to go back to the original word and look at the pair partition there. Which generator is eventually going to end up with which inverse to cancel out to give you the identity, right? And that's the pair partition we'll be able to assign for each word. So I really wanted to talk about, I wanted to show that this normal form is unique, and the way I was able to show that was to use a technique that lots of people use in theoretical computer science called abstract reduction systems, which shows you how you can show that a particular normal form is unique. I found this very rigorous and very nice. So anyway, I found it very useful to show what I wanted to. But maybe I should, in 2 minutes, skip to step 3, which is, so for every word that evaluates to the identity, you have a pair partition. The next step is to say for every pair partition, how many words evaluate to the identity and are assigned to this pair partition. So that's sort of the converse of this, but you're counting how many words do this. And the thing is, again, I'm going to skip a few slides. The thing is that you don't need an exact value for this number, nd and pi, because you're going to look at the limit as n goes to infinity. So it's good enough to find lower and upper bounds. But what you can do is to find a lower and an upper bound which doesn't depend on the pair partition pi. So you just get something here, which approximately looks like this thing here just looks like n choose d over 2, because everything else there doesn't really contribute in the limit as n goes to infinity. And similarly, this factor here is just close enough to n choose d over 2, so that when you do a bunch of cancellations on both sides, again, let me go with this and then go to the next slide. I know I'm skipping a lot of details. I am really sorry. I have a lot of calculations here, but I'll just go to the last slide, which is what gives us our bounds. What you'll end up with taking limits as n go to infinity is that the limit of the dth moment of Sn lies between the sum over all pair partitions of just the constant, because everything on that side has just been cancelled out, and similarly on the right-hand side. So you get to the limit, you get this, the limit of these moments to be sandwiched simply between the number of pair partitions of D and the number of pair partitions of D. So it's equal to the number of pair partitions of D, all pair partitions, which is D minus 1 double factorial, which is exactly the dth moment of corresponding to the random variable with the normal distribution. I know I pretty much skipped everything there in the proof. I am sorry that I spent too much time on the first half of the talk. But the essential thing to take away is that you can take a word and bring it down to this unique normal form and use that to assign a pair partition to any word, which becomes the identity. And for every pair partition, you can estimate how many words are going to fall into that basket. And then applying limits, you end up getting that the limit of the dth moments is simply D minus 1 double factorial. So just a recap is that F is generated by these generators satisfying these relations. You have a naturally defined sequence AN which comes from the generators GN. Then the sequence SN, these rescaled averages, will converge in distribution to X, where X is a normally distributed random variable of mean 0 and variance 1. So I know I completely sped through that last bit, but I just want to say, especially I just want to go over this point 1, which says that I mentioned this generalized CLP for exchangeable sequences which satisfy the singleton vanishing property, but the sequence AN does not satisfy those conditions. It's not exchangeable and it does not satisfy the singleton vanishing property. So it's not something that fits into that basket. But on the other hand, maybe it's not surprising. It's because the relations of F, they're almost commuting in some sense, even though they're not commuting, but they look like they're commuting. And recently, ILO extended this central limit theorem to Brown-Thompson groups, where the relations are very similar, but slightly more general. So GN, GK is GK, GN plus P minus 1, where P can be anything greater than or equal to 2. So again, there's a slight shift in the larger index, but the shift can be more than the case that we looked at. So I do apologize for being a little disorganized, but I'll stop here. I'll go to the next slide, which says thank you.
Okay.
Yeah, I really like the very end, and you gave a great overview. And people, you're welcome to send me the slides so people can look at them at a leisure. But I have a quick question about, you have this sandwich between the upper bound and lower bound in the limit.
Yes.
Can you actually compute for special cases this quantity, capital N of d and pi for specific pi? Is it hard to compute?
It's possible that you can compute it. I think I just I didn't bother because I was only looking at the limit. But I don't know for specific like for small values of d, so for words of small length, I think you can probably say exactly what it is quite easily. But after a point, I was just trying to find bounds so I can see what the limit is. But it is, I think it should be possible for at least for smaller values of d.
It was beautiful. It's very combinatorial. And for the multivariable extension, would it be also with arbitrary correlation matrix, or would it be independently normal?
Yes, the multivariate case. The thing is that so honestly, I'm still trying to think about how to formulate this in the correct way. So if I'm looking at, so how do I make this two-dimensional, for example? So would you look at the first n generators and then the next set of n and then mix these up to see when you can get the identity? So that's one way to think about it and see what the limiting moments are. But I haven't gotten very far with this question.
Well, it's a very good question.
Can I ask, does this Thompson group, I mean, can you realize that there's some kind of inverse system of finite groups, some kind of inverse limit? I mean, I ask that because, like in this asymptotic representation theory of the infinite symmetric group, one of the crucial tools is that you can write these virtual permutations as some sort of inverse system of finite symmetric groups, right?
Right. So, like as an inductive limit or some kind of direct limit. Or sorry, I didn't hear you.
Sorry, you're muted, Jane.
No, I think you're still muted. Could you? You're not muted now, but I think we still can't hear you for some reason.
Yeah, I guess.
Oh.
Yeah, I think we can hear you now. Yeah.
So in the case of I think it's an inverse system in the case of the symmetric groups. You have a kind of equivariant projection from Sn plus 1 into Sn, and then that's how you define virtual permutations. But so can you realize the Thompson group somehow like that?
Like, can you get a sequence of subgroups which somehow
of finite, preferably finite things, yeah.
I'm really not sure, to be honest. I'd have to look. I mean, somehow the way the relations are is that if you only take, let's say, the first two, and then you look at the relations, you'll end up having to have the third generator because, you have G2, G1 is G1, G3. So if I took G2, G1, G1 inverse G2, G1, I would end up getting G3. So that might force that the next generator is also there, if that makes sense. So I'm not sure how you'd form these subgroups. I'd have to think about it. I'm not very sure.
Another quick question is about the second bullet on this slide. These Brown-Thompson groups. Is the limiting distribution still normal for other values of P?
Yes, that's what was shown in this paper.
Mm-hmm.
So that was maybe like a year after I had my preprint up. ILO showed that it extends to all of these groups as well.
Interesting. Okay.
So again, it's kind of commuting, but it's just the index of one generator is increasing.
So instead of non-clustering pairs, you have something more general. The combinatorial structure that comes up, is it similar to non-crossing partitions and crossing partitions?
In this case, all pair partitions. Excuse me. All pair partitions seem to contribute, not just the non-crossing ones. So it's like the classical setting.
Yeah.
So.
Okay, great. Any other questions? Eugene, you're unmuted. Maybe you wanted to ask something, or?
No, thank
No,
you.
okay.
No, sorry, I didn't start my mute.
Okay.
Yeah, I'm just puzzled with this summation over permutations. Doron, you know how to handle those sums? You ask the question, what is the sum?
Yeah, it'd be interesting to find the middle, right? It would be interesting to find
here.
Explicit expression, not just the limit.
Yeah, do you know how to handle those?
I'm not sure. I have to look at the actual.
Yeah, I'm puzzled. That's why.
Yeah, it's a good question. I began to look at it, but it's only a tangent, and the proof is beautiful. And for this, you only need the limit, and the sandwich is very nice.
Okay, Jean Scott, I think, do you have other questions?
I just wanted to get a copy of the notes of the slides, if possible.
Hopefully, be posted soon in the website.
Yeah, I'll just email it to Stoyan.
Thank you.
Okay.
Yeah. We will upload them as usual, and post a link with the link to the recording. Yeah. Well, thanks everybody for staying, and thanks to the speaker, of course.
And the next talk is in 2 weeks. Thank you.
Yeah, have a break here at Rutgers. All right. Thanks everyone. Bye-bye.
Thank you. Bye.
Good night. Thanks for doing it so late.
No, thank you. Thanks very much. Bye-bye.
Definitely.